In this video, we're going to cover Chapter 6, Section 2. Again, remember in the last video I mentioned to you that ultimately we are getting ourselves ready to discuss exponential and logarithmic functions. So in the first section of 6.1, we discussed the composition of functions. And in this section, we're going to discuss one-to-one and inverse functions. And then we'll be armed and dangerous and be able to learn about exponential and logarithmic functions. Now, the topic from 6.1 of compositions we're going to see today in 6.2, and we use that tool to define functions that are inverses. All right, so first, let's discuss the concept of a function being one-to-one. What does that mean? So the definition in the textbook basically says a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. Now basically what this says in layman's terms, right, is that each output in the range can only come from distinct inputs from the domain. All right, let's see what that means. Okay, so here's an example, very generic visualization of a function. In this representation, we would have, first of all, this would be a function because each x value only goes to one y value. And this also would be one-to-one because each y value comes from one and only one x value. So we would call this a function, and we would also say that it's one-to-one. Now in this example, we have a representation of a generic function, and again this is a function because for each x there's one and only one y. For this x there's one and only one y. For this x there's one and only one y. However, this example is not one-to-one because this y value comes from two different x values. So I would not call this function one-to-one, right? Not a one-to-one function. Right, and then this last example, this is not a function, right? So this x has two different y values. So that's not a function, right? But technically it would be one-to-one because this y comes from only one x, this y comes from only one x, this y comes from only one x. So again, this is a function and, excuse me, this is not a function, but it is one-to-one. So that's the definition of one-to-one. All right, so let's look at a specific example. So here is a mapping, right? This is a relation technically, and in this relation, in the domain, we have states, and we map the state to a population. So technically, this relation here is a function because each x goes to one and only one y value. This would also be one-to-one because each y value comes from one and only one x value. Right? So this relation is one-to-one. Right? Now in this example, this is a function because this x goes to only one y. This x goes to only one y. Right? Each x goes to only one y. However, this is not one-to-one because this y comes from two separate x's, right? This y value comes from three separate x's, so we wouldn't say that this is one-to-one. Right, and of course, most of what we do in this course is graphing, and we're going to introduce the idea of the horizontal line test. So remember that for functions, we tested functions with the vertical line test. What we're going to do with graphs that we are testing for one-to-oneness, we're going to use what we call the horizontal line test. So this is just a visual way to determine whether for each output it comes from one and only one input. Right, so here's an example of a function that's not one-to-one, right? Because for this output of y, it's coming from two separate inputs. So because this graph fails the horizontal line test, we're going to say this graph is not one-to-one. All right, so for these two examples, we're being asked to determine whether these functions are one-to-one. So this first example, we have the square function. And if we think visually, right, the square function is the parabola, and we see that the parabola would fail the horizontal line test. So we would say that the function f of x equals x squared is not one-to-one. And then if we think of the standard cube function, right, there's the graph of the standard cube function, and we can see that the cube function would pass the horizontal line test, right? Every horizontal line that I draw would intersect the graph only one time. So we would say that the cube function is one-to-one. All right, so quick question for you. Is this function graphed to the right one-to-one? And good answer if you said no, it is not one-to-one, right? So this graph would fail the horizontal line test multiple times. So we're going to say that this function is not one-to-one. All right, now let's talk about the next idea here, which is called we're going to determine the inverse of a function. All right, now here's the formal definition of an inverse function. Well, basically what an inverse function is if the function f maps us from domain to range, then the inverse will take us backwards, right? So the correspondence from the range back to the domain, we're going to call that the inverse function. All right, so in other words, the inverse undoes the original function. And then what we're going to do in this section is introduce a new notation, and it's kind of hard to see this here, but so if I have a function f, what we're going to do is we're going to denote the inverse. We're going to put a little -1 exponent. That's supposed to be a -1 exponent there. So f to the -1 power denotes the inverse of the function f. All right, so again, here's a visualization of what we just defined. So let's suppose this is domain of the function f, and I have an input in the domain, right? So here's an x value, and the function f maps to some y value in its range. So f inverse is going to map this element back to the starting point, right? So for example, we actually know a couple inverses that we've been dealing with for quite a long time in our mathematical career. So if I think about the square function, right? Suppose this is the number 2. If I take the number 2 and I square it, that maps me to the number 4. Because that's 2 squared. And then to undo the squaring, I would use the square root function. So if I have the number 4 and I square root 4, that takes me back to where I started at the number 2. So the square function would be the mapping of f, and the square root function would be its inverse. Kind of an example of that visualization there. All right, so if we come back to the example we looked at a second ago, right, here was the mapping, right? We had a function that was one-to-one that mapped each state in the domain to its population in the range. So if I wanted to create the inverse function, what I'm basically going to do is map backwards, right? So here's the original function mapping from the state to the population. Here is the inverse function mapping from the population to the state. Now, if this is my original function f, then this is my function f inverse. I just want to point out to you here, right, the state is the domain of the function f. The population is the outputs, the range of the function f. And then for the function f inverse, those things are reversed. So now the populations are the inputs, the domain of the function f inverse, and then the outputs of the inverse function are the states. Right? So it's just kind of interesting to point out to you here, right? What was an input for the function f is now an output for the function f inverse. So if I was going to state the domain and range of the inverse, right, the domain are all of these values and the range are all of these values for the inverse function. So to just look at another example to kind of hammer that idea home. So let's suppose this is a function. Here's a function. We have a bunch of ordered pairs, right? So here's an x value, here's its y value. Here's an x value, here's its y value. Here's an x value, here's its y value. so on and so forth. So if this is the function f, the function f inverse would go in the other direction, right? So in other words, this point, I'm going to interchange the domain and range, right? So the output is now the input, and it maps to the original input, right? So let me grab my digital marker here, right? So if f maps me in this direction, here's the function f, then f inverse is going to map me in that direction. There's f to the -1 power. There's f inverse, right? So f inverse, so this is the input for f inverse. That's what I have here. And then this is the output of f inverse, and that's what I have here, right? So input to output, and then now the output becomes the input. The input becomes the output. That sounds a little weird, but that's the inverse function, right? So I just literally interchange x and y, and that creates the inverse function, the mapping backwards. All right, now of course in this class, right, we're going to deal with equations and their graphs. So let's look specifically at an equation, right? So I just want to illustrate this a little bit deeper with an equation. So instead of using the square and the square root, what I'm going to do is use the cube and the cube root, right? So if we think of the cube function, if I take -3 and cube it, -3 times -3 times -3 would be -27. If I take -2 and cube that number, -2 times -2 times -2 would be -8. 0 cubed is 0, 2 cubed is 8, 3 cubed is 27. So let me think about the cube root function, right? So if I plot some points on the cube root function, I apologize for this little weird line here, right? So if I think about points on the cube root function, right? If I take -27, I cube root that number, that maps me to -3. So I'm going backwards here. So if I take this number and cube it, the cube root takes me back. Right? So here's the input to the cube root. Here's its output. Right? And then again, if -8 is the input to the cube root, -2 is its output. Right? And 0, and then cube root of 8 is 2, cube root of 27 is 3. Right? So again, it's just trying to visualize this with an equation. Right? So again, if 3 is the input to the cube, 27 is its output, then if 27 is the input of the cube root, then 3 will be its output, right? So we can see kind of what we saw on that prior slide. If this is the x and this is the y, when I flip them around, this is now the x, this is now the y, I'm creating the inverse function. And we know that the cube and the cube root are inverses. They undo each other. Right? The cube does something, and the cube root comes back and undoes that. So a couple things to point out to you here, right? Let's introduce some notation. So let's pick this point right here. So if 2 gets plugged into the function f, then 8 is its output. Right? So if 2 gets plugged into the cube, 8 is its output. So f at 2 equals 8. And then vice versa, if 8 gets plugged into the inverse function, then 2 is its output. Right? So I'm just writing this in function notation. So f at 2 equals 8, then f inverse at 8 equals 2. Right? So again, this is just pointing out to us that if 2 is in the domain of the function, then 2 will be in the range of its inverse. And vice versa. 8 was in the domain of the inverse. That's because it was the range of the function. Right? So again, 2 is in the domain of the function. 2 is in the range of the inverse. 8 was in the domain of the inverse. That's because 8 was in the range of the function. And we could also write that in this fashion. Right? So this looks kind of weird, but let's think about what we used in 6.1. Remember, we used that composition notation. So in other words, let's notice that if I do f composed with f inverse at 8, so if we were doing this composition back in 6.1, this is the first thing that I evaluate. I evaluate f inverse at 8. So what is f inverse at 8? So f inverse at 8 is 2. So I'm going to replace the inside here with 2. So in this composition now, f composed with f inverse at 8 becomes f at 2. And what's f at 2? Well, if I plug 2 into the function f, I get 8, and there's that result. So this is really cool, right? This shows you in composition form that f and f inverse undo each other. This is pretty cool. So f and f inverse literally like wipe each other out. They undo each other, and the input is the output, right? So the 8 comes out of that result, right? And this illustrates that they undo each other. All right, and here's what the book shows you, just to tag on that idea. Here's what the book shows you. So I input an x value, I apply the function f, I get an output. And then when I apply f inverse, I undo that work, and I get just the x back. So whatever my input was, f does it, f inverse undoes it, and I get the original value back. Right? If I go back to that last slide, if I plug 8 in, f inverse does something, f undoes that, and I get the 8 out. Right? That's what we see there, right? So mathematically, we're using compositions to describe functions undoing each other. So if two functions are composed, right, and they're inverses, they're going to undo each other, right? And I'm going to get just the input comes back to me, right? All right, now the book describes for you basically the same thing in like 3 different ways. So what we noticed on those prior slides was if the point AB is on the graph of f, then the point BA is going to be on the graph of f inverse. Right? And on that prior slide, we saw that, right? Here's the point 2, 8 on the graph of f. I interchange domain and range, and 8, 2 becomes a point on its inverse. So again, in general, if AB is on the graph of f, then BA is on the graph of f inverse. Now this is what we wrote, same thing, but now I'm using function notation, right? So if A is in the domain of the function, A is then in the range of the inverse, right? And again, if B is in the range of the function, B then becomes the input, the domain of the inverse. So really these two asterisks here are saying the exact same thing. This one is just speaking about ordered pairs. A is domain, B is range. This is just using function notation. A is domain, B is range. So AB becoming the point BA is speaking in terms of ordered pairs, right? F at A equals B, F inverse at B equals A is saying the same thing, just using function notation. And again, here's the same conversation said in a slightly different way. So the domain of the function will become the range of the inverse. Right? So again, the domain of the function becomes the range of the inverse. And then vice versa. The range of the function will become the domain of the inverse. So all 3 of these things down here really say the same thing. Or just saying it in a slightly different way. And so this slide points out to me what we could technically call, properties of inverse functions. So properties of inverse functions are that when I compose them, they undo each other. Points AB become point BA on the inverse. Right? F at A equals B means F inverse at B equals A. And domain and range switch roles. So these, we could technically call them properties of a function and its inverse. All right, so let's illustrate this composition thing a little bit more with a couple more examples, right? So I just want to illustrate this a little deeper. So and a couple slides ago, right, we talked about the cube and the cube root being inverses. So let's show that the compositions would undo each other, right? So if I do G inverse composed with G, right, the first thing I'm going to do is evaluate the inside function G. And G is the cube. So I'm going to replace G with the cube. Right? So now the cube gets plugged into the inverse function. So I'm going to take this and plug it right here into the inverse function. So I'm going to cube root the input. So I'm going to cube root the input right here. Here's my input. I'm going to cube root it. And we know that the cube root undoes the cube. And we get just x out of that composition. And if I go the other direction, the same thing. If I do G composed with G inverse, I'm going to get G evaluated at cube root of x. That's the cube root cubed, and those undo each other, and I get just x. So here's a quick illustration of that definition, let me go back here, of that prior slide. The function and its inverse undoing each other. Now letter B illustrates the same thing just with different equations now. So letter B says let's consider f to be the line 2x plus 3 And let's consider its inverse 1/2 times x minus 3. And let's show the decompositions undo each other. So if I do f inverse composed with f, right? Here's f, 2x plus 3. So that's going to get plugged into the inverse function. So here's me plugging it into the inverse function. 3 and negative 3 subtract out. So I just get 1/2 times 2x, and that simplifies to x. Right? And then I could do the inverse, the composition in the other direction. So if I do the composition in the other direction, right, the inverse function is 1/2 x minus 3. And then I'm going to plug this into the f function, and I get 2 times the x plus 3. And then if I distribute the 2 here, right, the 2 times 1/2 is 1. So I get 1 times x minus 3 plus 3, the 3's cancel, and I get just x. So here's 2 examples illustrating that prior definition where we do the composition. And this again stems back to 6.1 where we learned about compositions. And again, this further illustrates to me that whole idea of undoing each other. So 2 functions are undoing each other. Their compositions return the expression x. All right, so for the sake of time here, I'm going to move a little quick through this example. But again, feel free to pause and absorb this stuff as I talk about it. So here's a problem that says verify that these are inverses. And so basically what we're going to do is what we did on the last section, the last slide. We're going to compose them. So the first composition is, let's do f composed with f inverse. So I'm going to plug in f inverse, that's 1 over x plus 1, and then that's going to get plugged into the f function. So I plug that into the f function, the 1 and the minus 1 cancel out. I get 1 over 1 minus x, so I flip and multiply this, and I get just x as the result. So I can see that when I do the composition in this direction, I'm getting x as its output. And then let's do the composition in the other direction. So let's put f inside of f inverse. So here's my function f. I'm going to plug that into the inverse function. And then I'm going to simplify that expression. And I'm going to get just x as that result. Now again, 1 over something, remember this is really the reciprocal. So I flip and multiply this, and that's where this expression comes from. The 1's cancel out, and I get just x. So I'm showing that the functions undo each other, and therefore verifying that this function and this function are inverses of each other. All right, now we've been talking a lot about ordered pairs, right? Domain and range switching roles, the point AB becoming the point BA. And then the last example we talked about the composition itself, or how would we work through that composition. Now let's focus visually for a moment here. So first of all, just to point out that if we have the point AB on some graph, and then we interchange domain and range and create the point BA, right? Visually, those 2 points are mirror images about the line y equals x. So what we're going to notice here in just a second, right, is that the function and its inverse will be mirror images over the line y equals x due to the symmetry that we get by interchanging domain and range. So here's a theorem in the section that says the graph of a function f and its inverse are symmetric to each other about the line y equals x. So here's a visualization with multiple points, right? So let's say this blue graph is the graph of a function f of x, and if I take the x and y value and interchange them, I'm going to create the function f inverse. So here's the inverse function, and it will be the mirror image, right? It's symmetric to the function f over the line y equals x. All right, now I strongly encourage you to take out your TI or use Desmos to do this, but let's suppose that we want to graph the prior examples that we did. So remember in the one example we had x cubed and cube root as inverses. So if we were to graph the cube and graph the cube root, and we also graph the line y equals x, here's what that would look like. So here's the cube function right here, and then here's the cube root function right here. And we can see, here's the line y equals x, right, that those 2 graphs are symmetric to each other about the line y equals x. Right? Again, please feel free to do this on Desmos or your TI, right? Pause the video and graph these. Here was the other function that we composed, 2x plus 3 and then 1/2 x minus 3. And if we graph those two functions, we see their mirror images over the line y equals x that right here. So we see this symmetry over the line y equals x. And that's always going to be true. So a function and its inverse will always be symmetric to each other over the line y equals x. All right, let's take that idea a little bit further here. So there's a couple problems in my math lab where they basically say, you know, construct the graph of the inverse. So they don't even give you an equation. All right, so on the prior slide, we had the equations, but what if we didn't have the equation? What if we only had, you know, points on the graph? Well, you know, this isn't difficult, right? Here's what we're going to do. We're going to interchange domain and range. So for example, here's the point on the function, the point -2, -1. So we're going to interchange domain and range, and we're going to plot the point -1, -2. So there's the point -1, -2. And then I'm going to take this point, -1, 0, and I'm going to interchange domain and range and plot the point 0, -1. So here's 0, -1. And then, you know, one more point on the graph, 2, 1. I'm going to interchange domain and range. I'm going to plot the point 1, 2, and there's that point there. Right? And then, you know, I'm going to connect the dots. So if I connect the dots, right, there's the graph of the inverse function in red. And again, we are seeing the symmetry to the line y equals x. So even without the equation of the function, we are able to generate or build or construct the graph of the inverse by knowing that for a function f, domain and range have to switch roles to generate what we call the inverse function. All right, so let's take a look at the last piece of this conversation. So we've talked about, you know, if we had points, how we could generate points for the inverse function. We talked about, you know, if we had a graph, how we could generate the graph of the inverse function. Now let's talk specifically about if we have the equation, how do we create the equation? So for this example, right, here's what we're going to do. I'm going to illustrate this with a specific example. Suppose I have the function y equals 2x plus 3, and I want to find the equation of the inverse. So remember, what we said was domain and range have to switch roles, right? So, well, first of all, I guess the problem asked for the domain of the function, right? So this is a line, the domain is all reals, and in fact, the range is all reals as well. All right, so let's move on then to finding the inverse. So we know for an inverse, the domain and range must switch roles. So what I'm going to do is I'm going to take my original equation and I'm going to literally change the domain and range. So where I had range values, I'm going to make them domain, which is what we use x, that symbol, right? And where I had domain values, I'm going to make them the range. So technically, this equation right here is the equation of the inverse. I technically don't need to do anything. I'm done. However, that's not what we do in this class, right? We like to represent y as a function of x. So in this process, right, first thing I'm going to do is interchange the x, y symbols, right? I'm going to interchange domain and range, and then I'm going to solve for y. So the next step then is to solve this equation for y. So I'm going to subtract a 3 to the other side, then I'm going to divide both sides by 2, and then here's my inverse, right? So technically this is my inverse written where y is a function of x. So the last step I'm going to do here is I'm going to replace the y variable with the inverse notation, and I'm going to call it f inverse. So if this was the function f, here is the equation f inverse. Right, and if I'm listing domain and range, I could cheat a little bit. The domain of the function will become the range of its inverse, and the range of the function will become the domain of its inverse. So I could just switch those around, and there's my domain and range of that inverse function. Right, and then, you know, maybe a way to check our work. This is a really nice way to check visually. We could take out our graphing calculator or use Desmos, and we could graph the function. We could graph its inverse and just make sure that it's symmetric to the line y equals x. And that's a good way to check our work here. All right, so the book shows you the steps that I just illustrated. They say, number one, interchange the domain and range variables. And technically, this equation defines the inverse, right? But what we're going to do is solve for y and to get it a function of x. And then we're going to use the f inverse notation. And then step 3 says check. Now, what the author says you should do to check is do the composition. And I'm suggesting that you just graph them and check. All right, so let's look at one more example here. So let's suppose we're given this function, f of x equals 2x plus 1 over x minus 1, right? So we have a rational function. We know that we can't have division by 0. So here's the domain of my function f, right? All reals except x equal to 1, right? So let's suppose we're going to find the inverse equation, right? So I'm going to rewrite the equation so that it has the letter y for the f of x, and then I'm going to interchange domain and range. So every place I have a y, I'm going to write an x. Every place I have an x, I'm going to write a y. Again, technically, this is the inverse equation, but what we want to do is solve for y. So to solve for y, here's a couple different ways to approach this. I'm going to multiply both sides by y minus 1, so I can get rid of it on the right-hand side and move it to the left-hand side. So I multiply both sides by y minus 1. And then in order to gather all the y's, I'm going to distribute the x variable here. So I'm going to write x times y minus x on the left-hand side. Then I'm going to gather all the y's on the same side. So what I'm going to do is I'm going to take this x, add it to the other side. I'm going to take the 2y and subtract it to the left-hand side. So I get that step. Now I'm almost done, right? So if I'm solving for y, then the next step is going to be to take this y value, y expression and factor it out. So if I factor out the y, I'm going to have y times x minus 2. And then the last thing I'm going to do is divide this over to the other side so that I can isolate my y variable. So here I have solved for y. This is my inverse function, so I'm going to use the inverse notation and call it the inverse function. So for this example, instead of graphing the two initially, I used the instruction on that prior slide, and let's do the composition. So if we do the composition, f composed with f inverse, right, here's what that would look like. Right, so if I take f composed with f inverse, my f inverse is x plus 1 over x minus 2. So that's what's getting plugged into the function f, right? So this expression is going to get plugged into both of these x variables in the function. So that's what I do there. And then to clean this up, what I did was I multiplied the numerator by x minus 2. So if I multiply the numerator by x minus 2, it will distribute here and cancel, and then it will distribute here. And then I multiply the denominator by x minus 2 as well, so that it distributes here and cancels, and then distributes here, and I get that result. Right, so the x minus 2 distributes here, the denominator wipes out, I'm left with 2 times x plus 1, and then I have the 1 times x minus 2. Okay, so again, just showing you what I did was multiply top and bottom by x minus 2, distribute to both terms, and I get this result here, and then distribute downstairs, and I get this result here, and it gets rid of that compound fraction for me. And then if I continue cleaning that up, right, I'll distribute the 2 and distribute the negative 1 and then gather all the like terms. I get 3x over 3, which is just x, right? So this is what the book is suggesting you do to check. And I would suggest that you just graph. I think it's a little bit easier to graph. Right, and again, I would encourage you to take out your TI or use Desmos and graph those functions. It's just something I want to show you real quick, which hopefully is obvious, but if not, let's discuss it here. Here's the original function right here, and this is a rational function, right? So remember, division by 0 gives me vertical asymptotes. So x equals 1 is a vertical asymptote here. And then the horizontal asymptote of this function, like we discussed in chapter 5, the numerator's degree is 1, the denominator's degree is 1. So the coefficients, 2 over 1, gives me the horizontal asymptote. You can see y equals 2, this red line, is a horizontal asymptote. Now hopefully it's not too surprising, but maybe it is, and that's cool. We're pointing it out to ourselves. The horizontal line will become the vertical asymptote on the inverse. So if y equals 2 is the horizontal line, x equals 2 becomes the vertical asymptote. And then vice versa. X equals 1 calls division by 0 here, right? That was my vertical asymptote. So then y equals 1 becomes my horizontal asymptote for the inverse function, right? So what's in the domain moves to the range, right? And what's in the range moves to the domain between the function and its inverse. All right, so the last example I'm going to show you here real quick, and then we're done, is with the square function. Now, this whole section talking about inverses, we know inverses undo each other. So if we think about the square function, its inverse should be the square root function. However, I just want to point something out to you here where we encounter some unique difficulty. If I think about the square function initially, the square function is not one-to-one. Right? So if we look at its graph, right, it fails the horizontal line test. It's not one-to-one. Now, technically what that means is if we find the inverse of the square function, its inverse fails the vertical line test and really isn't a function. So here's what we do, and you'll notice in the instruction here, they say find the inverse if x is greater than or equal to 0. So if I take the square function and I restrict its domain to x being greater than 0, that cuts the graph in half, right? So if x is greater than 0, I get this half of the parabola, and now it passes the horizontal line test. And then if I take this graph, reflect it over the line y equals x, I create its inverse, which we know that to be the square root function, right? So here's the graph of the square if I restrict its domain and it is one-to-one, and then here's the graph of the square root that now passes the vertical line test, right? So y equals x squared is the equation. I interchange domain and range. I take the square root of both sides. Technically the plus or minus is what gives me the upper and lower half. Right, so here's the positive square root, here's the negative square root, and that's not a function, right? So we want it to be a function. So when we have the plus or minus a square root, we're going to take the positive root because that is the one that's the function. Right, and then we could check our work and we can see that the compositions undo each other. So when I compose the square and the square root, we get just x out of that result. Right, and then if we graph the two functions, again, we can see that they're symmetric. All right, so again, just to summarize what we discussed in 6.2, we discussed one-to-one functions, right? We discussed how if a function is one-to-one, then it will have an inverse that passes the vertical line test, right? We talked about the domain of a function becoming the range of its inverse, and the range of the function becoming the domain. We talked about we could compose the functions and they undo each other. Right? The graphs are symmetric about the line y equals x, and then we talked about that process for finding the equation of an inverse. So as always, if you guys have questions, please post in the discussion board, and I will see you in the next